Did you hear the recording in progress sound? Yes. Okay. Well, thank you. We're then ready to continue with our class. So before we start, I want to start asking you if you have any questions from yesterday. Anything at all? All right. I'm having trouble. Today's not the best day in technical terms. Okay, now it opens. So let's set back to where we were yesterday. And the idea is that yesterday we had this. Sorry, I need to open this first. QML notes. So I haven't updated the notes for me. Give me a second. Okay. I need the new version of the notes. Okay. Well, I'll do this. I'll briefly talk about what we've done so far. We have been exploring, we have been building up towards this fantastic system, which is first order modal logic. And we have done so by analyzing the model theory of each system. So first order modal logic has two fragments, so to say, first order logic and propositional modal logic. What we're trying to do today, and what we are going to start to see, is how we can combine those to make for a system. And as we will see, although mathematically it satisfies some of our desiderata, it's not that great when it comes to our philosophical intuitions. So we finished up yesterday talking about the contingentism versus necessitism and actualism versus possibilism debate. So are there any questions about those positions and about what we saw at that point? All right. So the idea today is that we start working towards the system, but first we need to talk about the Barkan formulas. So if you remember yesterday, if you remember what we talked from yesterday, we were talking about the three formulas that were important for us to understand the implications of adding quantifiers to a modal logic or modalities to a quantified logic. So the first thing we saw was this formula that is for all x, f of x. And the idea is there's going to be debate when it comes exactly to how to interpret the quantifier here. Because as we know, this means everything. But the question is, what do we mean exactly with everything? Do we mean everything, absolutely everything in the world? Do we mean just the things that are in this domain, considering we split domains, or are there things that are true in the world at the hand? And this comes basically because when we're doing first order logic, we never ask ourselves this question. But when we mix this with modal logic, then we get the question. The second issue we had to do with the Converse-Barkan formula. And the Converse-Barkan formula in this version that I'm presenting you says the following. It says that for all x, if for all x necessary f of x, then necessarily for all x, f of x. So the issue with this one is that if you are all for varying domains, so if you go for varying domains, you want to reject this. But if you are with fixed domains, you want to accept it. Now, the idea is that there's also another one, which is called the Barkan formula per se. This was the converse, this is the C. And the converse says that if it is possible, remember that I fill up this ones, f of x, then there is an f of x possibly, there is an x such that possibly f of x. And the intuitive reading for this was just what I told you, but the idea is to see and to judge whether from this, in fact, does follow this. So the example, for instance, like let's say that F stands for is a Martian. So it is possible that a Martian exists. So there is a world which allows for Martians. So the antecedent is true. But from this, can we conclude? So there is a world, let's call it W0, and there is another world called W1. And we want to say something here that while here in the domain, the extension of F is empty, but we're saying, hey, possibly there's another thing, it is possible that in another world we have that the extension of this predicate is not empty. But the problem here is that this implies that there is an object here. So here, there has to be something that it is possibly, so that is possibly a Martian. So there has to be something in W0, let's call it B, such that it is possible that it is a Martian. So that means basically that there has to be a corresponding object here such that for the other world that we have, in which he is possibly a Martian, then he is not a Martian here, but possibly needs to be. So much as with the other one, what we want to say is that people that do the varying domains want to reject this one, when people that want fixed domains want to accept it. Any questions so far? All right. So the idea of this is that we see a little bit why the converse Barkan formula and the Barkan formula are a little bit inevitable. So the problem is that when when logicians started discussing about this, it was in the 40s, in 46, that we didn't have a modal theory for modal logic. Does somebody know when the first completeness, so semantics for modal logic appeared? Does somebody know? Does it ring a bell to anyone? Well, it was in in 63. And in this years between the first papers that appeared on quantified modal logic in the 40s and the first discussion of first order modal logic from the modal theory perspective, which was in 63 by Kripke, there was a lot of discussion from the proof theory side, but not from the modal theory side. So the Barkan formulas appear as an intuitive way to relate quantifiers and modalities. And if you take a look at the converse Barkan formula, it looks intuitive if we do not consider anything about like how our intuitions about how the world really work, but just follow the logic. So we have that for all x, necessarily f of x, then box. So let's assume the antecedent is true. So assume what does it mean? This means it means that in the actual world, every object in the domain, for each, it is necessary that it has the property. What does this mean? It means that when you go and look at every other possible world, Oh, I see something in the chat. Oh. If you go and look at every other possible world, these objects have this property. So now we want to move to, let's move to another possible world, call it W1, and we want to check whether or not for all x, f of x holds there. But because the domain is fixed, the range of quantification in 1 is going to be the same as in the range of quantification that we had here. And the point is that since we know that for every object in the domain, we have necessarily f of t, then every t is f at w1, and therefore for all x, f of x is true at w1, and since this is arbitrary, completely arbitrary, we can conclude necessarily for all x, f of x. So you can make a similar argument for the Barkan formula, and the Barkan formula, remember that in this formulation, what we have is if it is possible that exists an x that is f of x, then it exists an x that it is possibly f of x. So you can make a very similar argument. There is an argument for this in the notes if you want to say it. But what I want to tell you with this is that if you go this very safe approach with the logic, you just assume a fixed domain, then you immediately are burdened by the Barkan formula. And what I want to tell you is that this hasn't sit well with a lot of people because a lot of people think that intuitively the Barkan formulas are invalid. So at this point, I want to ask you if you think or if you want to share what's your opinion of the Barkan formulas. Do you think they are intuitively true, false, or right now you don't have, are you not settled? So, seems sus, says Magnus. Great. Uh, yeah, seems sus, but from a philosophical perspective, I hope. I don't know if from a mathematical perspective also you share those suspicions. But anyone else wants to share what they think about the Barkan formula? All right. And with that being said, I want to give you a quick glimpse of what I expect to cover during the rest of these 2 weeks. And it is, I call it like the sea of semantics. And it is just to show you that there are a lot of options in which we can do this. So the first thing that we're going to do, and then so the seas of semantics. So this is just to pin down the fact that there are a lot of ways of doing this. And basically, the goal for a lot of people is to find a semantics which is complete with respect to S5. That means we're going towards something that we're going to call QS5. And why is QS5 our goal? Well, it has been debated for a lot of time, but the conclusion is that basically S5 is the strongest possible logic of necessity. And so philosophers have used it to reason about metaphysical necessity. We don't have to talk a lot about that, but it's just that you get it, have it in mind. So what we're first going to do today is do something that I call the naive approach. which is basically we're just going to merge the stuff into one. So we're going to take all that we do from the canonical model and we're going to move it with all that we had from the Henkin construction. We're going to see that that only takes us so far. Specifically, this only gives us logics which are complete with respect to this called something called universal axioms, or they're also called uh, forward-looking axioms. These are the axioms which their frame condition can be formalized using only non-negated universal quantifiers, or you can also say that in defining that those logics which can only look forward. So if you want the prime example of this, a logic that can only look forward is the basic logic, temporal logic T. But then after that, we're going to look at something that I'm going to call the necessitist semantics, which is basically quantified modal logic. So it's basically a version of higher order modal logic with identity. So the idea with this is that we start discussing how identity can be fit into a modal logic, into a first order, into a quantified modal logic. But the idea that we see like the most obvious way of doing it, and at the same time, it is not only the most obvious way of doing it, but it's also the most controversial way of doing it. After that, we're going to see some contingentist semantics, which it's going to be something that we're gonna something that has been discussed recently by Greg Russell, which is a direct answer to the contingentist, to the necessity semantics. And by the way, this is a very fresh, very new. So if you're interested, this is a very nice time to jump on the bus. Now, this is basically what we're going to do in terms of philosophy, and then we're going to enter into the more mathematical side of things. So the first thing that we're going to do next week is to change our framework from Kripke frames to Kripke sheaves. And Kripke sheaves are just a fancy name for a first order modal logic with identity, and identity is defined as cross-world identity, and that's very fun, and we're gonna learn all about it next week. Then we're going to see something called admissible models, which is going to be Robert Goldblatt's approach to this, which is very interesting, and it is very algebraically inspired. And then last but not least, we're going to do some tableau, which is by Fitting and Mendelssohn. And that is what I want to cover with you guys. So I want you to think of two things at this point. And the first thing is that most of you, we're going to have to do a presentation. And I want to tell you right now that the available topics for the presentation are everything except this one. You cannot take the naive approach for the presentations, unless you come up with a very interesting way of approaching it. But what I want to do, what I want you to do with the presentations is basically that you engage with the material and go a little bit deeper than what we see in these sessions. So what I mean by this is not that, so normally what I'm gonna give you are books, except in the case of Restal. And these books are very long, and I don't want you to stress out because you're gonna have to read a book next week and prepare a presentation on it. No, I just want you to fix on some of the most important aspects that we're going to discuss, and then that you can present to your fellow students what did you learn and engage in 1 week with some chapters of a book. So we can also discuss what do you want to do exactly, but just that so that you know, Next week, I expect for everyone that is going to do a presentation, I expect that you meet up with me formally or informally at least 2 times. One to discuss what you want to do, and the second one to discuss how are you planning to do it. And this is because if two people have the same topic, the idea is that you work or want to do in the same topic, the idea that you work in groups. You can also come to me and say, hey, Jasper and Y want to work on Kripke sheaves. That's great. Let's do it like that. But if you come interested and I see that there's a way of joining you for a topic, that's all right. Now, I said on the everywhere on the email on the website, it is said that the presentations have to last 1 hour and a half. That is not going to be the case because there is simply not enough material, nor there's not enough people for that. So the idea is that we have presentations for each system, or each group has a presentation of an hour and a half. But the idea is that this hour and a half is split between different people. There is an other option you can do, which is if you find very interesting semantics or modal theory for first order modal logic or whatever system of quantified modal logic that you're interested, and you say like, we didn't study this during the class, but I would like to present it and discuss it. Okay, yeah, you can do it. And if you find someone else that wants to do it with you, even better. But just so that you know, the summary of this is presentations. You are going to probably be working in groups, and if you're not working in group, presentation should be about an hour. But don't stress about that. And the people in the special project, I'll discuss with you later what we're gonna do with regards to the presentation and the assessment. Any questions so far? Do you have any questions on the assessment?
When do we have to decide uh, what presentation we are going to do?
So ideally by the end of next week. If you decide earlier, I mean, if tomorrow you fall in love with higher order modal logic, I mean, I can't fight that, so it's all right. Also, take into account that the faster you decide for something, well, the chances are that you're gonna get the topic, because it can also happen that four people want one topic, and I think that's not very productive. Does that answer the question? Why? All right. Any more questions about this? All right. So let's go and take a look at the naive approach. Okay, this isn't red, but I don't care. And the naive approach is going to be what we've talking about and we've been hinting at from yesterday and today. It is the most straightforward way of doing it, but it's not the first way people try to do this. The first, if you read Kripke's original paper from '63, you're going to be looking at a different meta language that is problematic for other reasons. But here we're just looking for a system which is complete with respect to the most intuitive way of doing a completeness proof. And that means you take the canonical model and you take the Henkin construction and you prove that if you have both, then you can make a you have a sound and complete system. Now, I told you yesterday that our system of first order logic didn't initially didn't have any constants, and that's because we added them later. But now we're going to work with languages that have constants ingrained in it from the beginning, and that is for an important reason that I'll tell you guys about later. But for the time being, let's just talk about the syntax. So the first thing that we have is, of course, the alphabet. Now let's call it the language, and that's it. So this is the language of first order modal logic, and we're going to have variables. There's going to be just object variables, and I'm going to represent them x, y, z, x1, x2, etc. Then what we're going to have is we're going to have some constants that are going to be the set C. And please notice that I'm writing this sort of fancy C because I'm going to use capital C for a class of frames later. And then basically I'm writing I either going to use uh yeah C's, or I'm going to use D. And D also is going to be like an arbitrary object. So we're going to have predicates, and this works just as in the previous one. We have logical symbols, and basically what we're going to have is, again, just negation and the conditional. We're going to have the universal quantifier, and we're going to have the box. Other than that, we have parentheses, we have point, and we have dots, etc. Now, we are going to have a different notion of well-formed formula here, because what we're going to have with respect to first order logic, first of all, is this. And this is going to be different to what we did in first order logic for the simple reason that we are going to create a new set, which is the set of terms. And the set of terms is a set. Sorry, no, there you go. Where the set T is equal to the union of the set of variables and the set of constants. So this is the first, maybe, and maybe only surprising thing. You have negation of stuff, you have conditional statements, you have quantified statements, and you have boxed statements. We have abbreviations, of course, for the conjunction, the disjunction, possibility, and existence. And I'm going to do the same trick that I did yesterday, which is basically I'm going to only define the universal quantifier and the necessity operator, but for the proofs, I'm going to use the possibility and the existential quantifier. So what we are interested in actually is, of course, for the time being, we're going to study the system QK. And what does QK mean? It means quantified K. So the it is determined by the class of all constant domain frames. So we're gonna have frames, and in those frames, we're gonna have constant domains. And we are naturally interested in other modal logics, but I'm going to assume that our goal for now is just to prove the completeness of QK, and then I'll explain you maybe how we do it for the other ones. So the problem, sorry, no, there's the notion of a first order counterpart, which is basically if lambda is a propositional modal logic, then its first order counterpart is the logic Q lambda, and that means that we have QK plus lambda. So this is because I don't want to start writing very long names for these logics. If I say if I say Q something, please assume it is a normal modal logic, right? All right, so we have all the rules. So if we remember the rules that we had modus ponens, we had generalization, we had necessitation, and we're going to have something, it's not going to be relevant, but just that you know, we're going to have something called predicate substitution. And the idea of predicate substitution is that you can substitute predicate letters uniformly across the formulas. If you have certain conditions for it, don't worry, everything is in the notes. But well, let's go and see the money. So we have a semantics for this, right? And the semantics consists of a set of worlds and an accessibility relation, and it is augmented by a single domain of individuals shared by all worlds. As I told you, we're going to try to do it first with fixed domain semantics. And then what we have is that the first thing we're going to have here, instead of having just a Kripke frame, we're going to have a constant domain Kripke frame. So whereas in modal logic, frames are a list of two elements. Here they are triples. So the idea of that is that a frame, constant domain Kripke frame, this should be a fancy F. Please think with me that it is a fancy F. We're going to have more things. So in a normal modal logic, you will only have this and this, but here you have the third element. So what is W? W is a set of worlds. I should try to move this here and then this here. It's a non-empty set of worlds. Then we're going to have R, which is again just a subset of the product of the world of the powers of the worlds, and D is a non-empty set. And this works much more like in the first order case. You just have an empty one, a non-empty one. But the idea now is that we use the constants to represent things within the domain. So in a constant domain model, what we're going to have is a family of valuations for each world. And in each, I'm going to tell you this and then I'm going to write it down. The idea is that at each world, we're going to have valuations that to each constant, they assign an element of that so that we can know and compare the valuations, which symbols are associated with which objects. And the idea of that is that we can have a more manageable way of using the universal quantifier. So the idea of this is that if you have a constant domain model, the idea is that you have, so I'm going to use, no, I used red M when it was a quantified model, is going to be the fancy F, and we're going to have B. The point of B in this case is that V is a family of valuations. What does that mean? So it's going to mean that for every world, you're going to have a valuation which is indexed according to that world. And for n-ary predicates, and let's this like this. Oh God. Every time I try to erase this and it doesn't work, I lose my mind. Sorry. So the idea is that for every valuation, which is local according to the world, you're going to assign elements. So you're going to, for every n-ary predicate, p to the n, this is n here. The idea is that whereas the interpretation of the object is going to be static, and you're going to be, sorry, where your domain of objects is going to be static and fixed, you always have the same objects, you are going to be able to make the predicates different across worlds. So the difference that we have with anything that we've seen so far is that we can now say in this world, in W0, we're going to have, so in W0, we can say that f, the extension of f is A and B. Okay, let's say that your domain is A, B, and C. And you have another world possibly accessible, who knows? And here the domain is only C. And here you have that, okay, yeah, so there's they have another, let's do it actualist. So there's another property G, which is only C, and there's another property here, G, which is only A. So this counts initially as a toy model of this because we only have 3 objects, and in both worlds, we have the same 3 objects. What we don't have is the same properties for all the objects. So what does it mean for us? It means that when we construct models, we're going to be able to shift how the properties that objects have. Before I move to the definition of truth, I just want to ask if there's questions so far. All right. So what we're going to do now is to define truth. So let's say that phi is a formula with constants from the domain, and we define truth inductively at a world like this. So we say that, oh, the m's should be in red, but so what is different here from the standard definition is 2 things. The first one is that we are all, God, I was going to use the highlighter. The first one is that we're using constants directly. So our atomic constant, so we're only making true formulas which are closed. That means that have a constant, they don't have free variables here. So in the previous thing we did with first order logic, we allowed still to have the free variables in our atomic formulas. Now we don't. So the idea is that we start using the tools that we now have to exactly do that. And the other one that is very important that you know is that again, the valuation is going to be dependent on the world you are. And of course, this means that this guy here and this guy here have to coincide. I hope that is sufficiently clear, but let me know if there are questions about that. So, on the other hand, negation is defined as expected. So as expected. Uh, so is our friend the conditional. This is just as expected. So is sorry. This is again as expected. But now the difference is going to be in how we manage the universally quantified formulas, because the important thing comes here, because it says for all D in the domain. And this is the other interpretation of the quantifiers that we have if we add constants from the start. And the idea is that we don't need the d-variant interpretation. We just can make this to say that that for every substitution instance of this formula using each of the symbols that we have, then that stays true. And the idea of this is that you notice how powerful universally quantified statements are in this logic, because it doesn't mean that it is, when you say for all x, f of x, you're not saying that for all of the x's in this world, they are true. You're saying for all the x's in all the worlds. So the quantifier is going to be very, very powerful in that regard. So if we go back to our toy model that we had, you're going to start seeing that you cannot make reference easily to all the objects in a particular world with the quantifiers. And you instead, when you use the universal quantifier, you're going to find that there are very few things that are going to be true in that model. For example, if I want to say that for all x, f of x, this will come out as false. Sorry, no. This is with regards to if in the model in world 0, I say for all x, f of x, this is false. But this is false even though there is another world, and this is the important point. I'm sorry for the mishap. This is false even though there is another possible world in which this object does have that property. So this is something that, of course, did not happen in first order logic, but the idea is that you start seeing how this works. Any questions? All right. now we're going to start looking at the completeness proof for this, but I want to make a quick break before that. So let's meet back at yeah, at 3, if that's okay with you. See you in 10 minutes. All right, all right. I hope you've had a great break. Hello, hello, Jasper. Hello. I forgot. I said your name incorrectly yesterday, Wojtek, but can you give me the correct pronunciation, please?
Now it was fairly correct. It's
Woj-
Wojtek.
Wojtek.
Yeah,
Thank you.
I think the easiest way to learn it is not mind the spelling.
Ah, yeah, but the J is a semi
Yeah, the
vowel,
J
right?
is read like an I and the W is read like a V. So
Okay, okay. Thank you. All right. So here's what I had in mind when I talked to you guys yesterday about the Vingo that we have. So the idea is that since we're going to look at so many systems and with so many properties, the idea is that we can have some fun with it. And the idea is that you go home, feel well, stay no. For this week, you stay home. I hope you are home in any case, and then you fill our bingo. And the bingo is going to help us analyze each system according to its properties. And as you can see here, there's a bunch of things, but some of these things we have not talked about explicitly. Some of these things are topics from the MRM course. So the idea is that I can tell you basically what it is, but if you're not sure of what something means, go look about it. This is my way of also telling you there are important things that I will not be able to cover, which I hope that you can do it in your, it takes you 5 minutes to learn some interesting things about this. So the idea of this is that, okay, you, if this was on site and on presence, this would be way more fun. But since we're stuck here because of today was 5 centimeters of snow, probably 10 centimeters of snow, but who knows? So the idea is that we feel you come with your bingo card filled for that way, that day, and then you and then we comment and we see what we got. So for instance, if I go here and say that this is the naive bingo card, we are going to try to fill up the spots. So I'm going to take some of this and then I'm going to tell you what it means and if we feel it or not. But at the same time, there's some that I want you to go look and look up to see if you can, like follow it back home. So the idea is that, for instance, we have standard Kripke semantics. And if we have standard Kripke semantics, you cross it. And in the naive system, it is. What it means that it's standard Kripke semantics that we have Kripke frames. And the frames can maybe have the constant domain thing and everything, but we are not doing anything to the frames. What does say and some of this you feel if they're connected to say. So for instance, we also said what does constant domains mean? It means that there is just one domain. All the worlds across the model have the same domain. So we cross this one. But then there is, for instance, this existence is a predicate. And we haven't talked about this, but the idea is that this is going to be relevant later. Because if existence is a predicate, is what we talked about yesterday about being a possibilist. Or some people in the uh, contingentism field are also very keen to this position. So constant domain existence is a predicate. We don't cross it. It is S5 complete. I don't know. Maybe. Who knows? Maybe we're gonna see it later. Then, for instance, requires free logic. What does that mean? Requires free logic means something that we're gonna learn to Friday, but it basically means that you can have worlds with which don't have every object, but you can still make reference to the objects that are in that domain. So you can in that world. So it was the opposite to the situation we were looking at, in which you cannot make reference to the things that exist in that world, but universal quantifier, you always packed up everything. Now, if you notice that I have this one here and I have this one here, so I mean, if you cross these two, quantifiers have mux commutes, right? Some of these are going to remain open, and this is where I want to show you also that these things that we're studying are still in development. And it is interesting if you see that there's some open topics on some stuff that it's still interesting to study from your presentation. Now, I will now be able to solve some questions about each of the items if you have them right now. But after today, you're on your own, and you're going to have to discuss them day by day. And the idea is that every day I choose someone randomly so that they share the bingo card. Is that okay? I hope that's okay, by the way. But questions about the items. I'm gonna give you 1 minute to look at them and maybe discuss them. There are a couple of mind traps there, which I hope you are able to identify. Booby traps, sorry. Right, if you're comfortable with this one. All right. Now I have good that you don't have questions. In any case, we will discuss. Remember, every day I'm going to choose someone randomly to share with us their bingo answers. Yeah, at the beginning of the lesson. And other than that, yeah, I wanted to ask you, so we are supposed to have class on Friday on site if everything works out. But I want to ask who would come, who thinks or is expecting or hopes to come on Friday on site because of the weather, I know that some people haven't been able to arrive to Amsterdam. Some people are going to try to do it, but at the same time, some people will not be here until for some weeks. So I'm going to ask you one by one. So Jasper, do you expect to come on presence from Friday on?
Yeah, I think I can come.
Okay. Wojtek?
I'm really dependent on NS trains, so I want to, but I cannot state it right now.
All right. All right. Ludovico, you already told me your situation, but has anything changed?
No, I'm stuck in Italy, unfortunately. Will
All right.
come by Tuesday. Like,
All right. Why? I don't know about you told me that you have an appointment, but
No, I was traveling and I won't be in Amsterdam. Uh, yeah. Till the end of the last week. So
okay, I
yeah, I
understand.
will joining virtually.
All
Yeah.
right. Jan?
I'm coming.
Okay. Timon?
Yeah, I will try to make it.
Isabel?
So I'm still in the US. I'm supposed to fly back to Amsterdam tomorrow, and my flight hasn't been canceled yet, but I'm not sure if it might be canceled. So yeah, I don't know yet.
Okay, let's hope for the best. In any case, this is all recorded and everything, so don't worry. And Magnus, you already we already discussed it, so don't worry. If there's any updates, just keep me in the loop. Andrea,
Only virtually, everybody.
only virtually. Switzerland is better, I guess. And Matteo told me that he's gonna come on Friday. All right, so this is because I was considering moving everything online, but since there are some people that are going to be on site, that's great. So we meet on Friday on the room that I sent you to. It was L012, which is a room that sucks, but we're gonna make the most out of it. Has anyone been in that room? I just hate it. Well, that being said, any questions from what we had so far? Oh God, I hate OS. Questions of what we had so far? There is something that I forgot to tell you about the system, and it is the point that if you take a closer look, the fact that we have these objects and we always have to refer to all the objects, that we have the objects in all the worlds and we have to fill it with the same objects every time, makes here an interpretation possible, a metaphysical interpretation possible of proper names. And that is the fact that they are rigid designators. So people from MRM, so Ludovico, Magnus, Jan, should be very familiar with what a rigid designator is. Maybe Jan, do you remember what rigid designators are? Or you want to very quickly look up if you don't remember, so that your more mathematically minded friends can know what a rigid designator is? Jan, do you remember?
Me?
Yeah.
No, I don't think I remember.
Okay. Ludovico, do you remember what a rigid designator is?
Well, rigid designator is proper name, and proper name that refers to a unique individual that exists in all possible worlds, basically.
Right, perfect. So the idea of this is that there is a theory of proper names that originated precisely from the work of modal logic, according to which proper names refer to the same objects across all possible worlds. And this interpretation makes that theory possible because you always have the same objects and they are committed to exist in every possible world. So with one constant, if you interpret constants as proper names, what you are doing is basically assigning to each object, each constant, an object in each possible world. And then you say that this is the same object. I hope that that is clear. Oh, why I also took MRM. Sorry, I forgot that I didn't include you in the list of people that took MRM. All right, questions from this, because we're going to move to the most important part, which is completeness. And so far I have not make a distinction between weak and strong completeness, just in case that you know. So sorry, I have a problem with my cats. No, he's right. Still not able to draw this properly. The idea is that you understand that this is the empty set. But there's a distinction in model theory that we sometimes do to talk about two versions of completeness. This is sometimes, as this is called weak completeness, and this is If I knew how to spell, that would be great. So this is weak completeness, and this is strong completeness. The idea is that, of course, strong completeness it's a harder result to prove because it's not as trivial. This is just saying that if something is a tautology, then it is derivable from the empty. So it is an it's derivable from an empty set. And this, on the other hand, as we talked about, is something different. We say that if there is a model that makes every small gamma in gamma true, then also makes this phi true. And if that happens, then we say that there is a proof, a derivation from gamma to phi in which every step of the process is either a member of gamma or is an application of the rules. So far, when I've referred to completeness, I've only talked about unproven strong completeness, but this is important for now because now I'm going to focus exclusively on strong completeness. So if I say that something is incomplete, I make that it is strongly incomplete, not that it is possibly weakly complete. And yeah, please take into account that because we're going to see some stuff which is incomplete, and I mean it in the sense that it's strongly incomplete. So for that, simply let's define strong Kripke completeness as a logic L is strongly Kripke complete with respect to a class of frames F if for every set of sentences gamma, if gamma is L consistent, then gamma is satisfiable in a model based on a frame F such that it is in the class of frames. And what I'm telling you is something that we was implicitly in the proof of completeness that we saw for modal logic, but now I'm going to put it more explicitly because we're going to see failures of this condition. And what you see here is that we have a class of frames, we have a set of sentences, we have a logic, and we have models based on a frame. And what this definition is telling you is that something is strongly Kripke complete with respect to a class of frames if every set of sentences, gamma, if it is consistent, and remember that consistency is a syntactic property, then it is satisfiable in a model based on a frame. Okay, so the method that we have, and we're going to see this completeness via canonicity, is a combination of what we saw with the Henkin method plus the canonical model method that we saw for modal logic. So if you remember, the protagonist and in both of them was the notion of consistency, that you build something that is consistency and is maximally so. In the case of first order logic, what we saw is that we need something that is not only maximally consistent, but it is also Henkin complete. No, sorry, I think we call it just Henkin, or it's also called saturated. For those that don't remember what saturation means, it means that for every existential claim that you also have an instance of it in which you say, so, oh no, let's say that saturated. So this is saturated if every psi such that this is an existential formula. Then if psi is gamma, then you have an instance of this in which you replace everything. You find a constant that satisfies that. This is what saturated, and if you have this for all the formulas, then it's saturated. And now I'm going to change a little bit the terminology that we saw from this construction to not confuse it to what we're going to do now. So we are going to say that, sorry, my cat is here. So I'm going to say the following. I'm going to define a special thing called an L-place. And an L-place is a set of sentences gamma in a... I skipped something, sorry. Importantly, and please don't forget it as I just did, that when you do this, when you add these instances, A or C as it is in the notes must be fresh. So the idea is that these are not constants that you have already used in your base language. If you remember, in first order logic, we said we introduce these constants at this stage. Here we're going to have two sets of constants. When you have this modified language, we're going to call this modified language LC because we have more constants. Now, we are able to define an L-place if it is a set of sentences in, let's say, in the set of formulas of LC, and it satisfies three conditions. The first one, that is very simple, so this one is something like L consistency, which is basically that it is consistent with respect to the base language. The second one is that it's maximally so. You already know what that means. It means that for any sentence, either it has it, for every formula, it's either in this set or it's not. But the last one is, of course, that it is Henke, that it is saturated. So for every formula of the form that I told you, that for every existentially quantified formula, there exists a constant that that witnesses the formula. So for every formula of the form there is a constant C from the new set of constants such that, and now I'm thinking that I totally could have not written this, given that I just wrote it. Well, in any case, now what we have to do is to do something very similar, but we are going to do, sorry, so what we just did is start up with our proof by doing something that we know from first order logic. Now we're going to come with the modal logic machinery, and then we're going to try to combine it. So the idea of this is that, please remember, well, first remember that we have a fixed domain and that this satisfies both converse Barkan and Barkan. So our canonical model this time around, so is going to be different, because remember that now we have the domain. So if we have a logic L, the canonical model is going to be m to the L, and we're going to have WL, the relationship, the accessibility relation, the domain, the set of valuations, and this are going to work a little bit as in the modal logic case. So the first thing we have is WL. And remember that in modal logic, what we had is that this W was the set of all maximally consistent sets. And I told you, think that for every model that you have a world, and in that world, you expand it to a maximal consistent set. And here, what I'm going to tell you is, imagine the same thing, but instead of expanding it to a maximal consistent subset, you're expanding it to a L place. And so is the set of all L places. So again, you can imagine this. This is not strictly correct, of course, but the idea is that every world, you buff it up with everything you can derive from the things that are true in it, such that are derivable in it, you buff it up, but you do not only keep whatever is maximally consistent, but it's also saturated. What did I write later? So R. R is the canonical accessibility relation, and is going to stay the same as in the modal logic. So for any gamma and delta that are in the set of L places, let's see if I can do this straightforwardly. Now it disappeared. No, I cannot do that. So very quickly, R, yeah, for any gamma delta in the set of L places, we say that gamma relates to delta, or is accessible from it, if and only if the set of necessary formulas of gamma belongs to delta. So from all the things that we've changed, this is the one that stays the most similar, as I already told you. Now, BL is just going to be the set of constants. Okay, now let's be more clear here. So we C union const. And the canonical valuation is VL, that says for any predicate P and constants C1 to Cn such that they are in DL. Then we have the following thing. So I'm going to use this abbreviation to mean the vector of constants. So this just means this over here. This means this, but I don't want to write it. This belongs in the evaluation of P with respect to gamma if and only if P, so P of C1, 2, 3 to the n belongs in gamma. And now we should be able to prove at some point, and this is where it becomes difficult, our truth lemma. And the truth lemma goes from our canonical model, so ML of gamma proves T F plus phi if and only if phi belongs in gamma. And the proof very straightforward, but this just basically shows at this point, we're not finished, because this basically shows that we have a canonical model, which gives us a mathematical structure that satisfies all our consistent formula. But what we have to show is that this system is strongly complete. So to prove completeness for a specific logic, let's say quantified K, we still need more than just a model. We need a model that obeys the specific frame conditions of that logic. And this leads to the definition of canonicity. And the idea is that now we're going to talk about the frame conditions of the canonical model. So a logic L is canonical. So canonical if the frame, so we have the frame the canonical frame, let's call it, underlying its canonical model, so the frame that belongs to the canonical model, validates the axioms of L. Or basically, it just means, oh, this is an L here. So it means that if you have a logic L and you say that in this logic, for this logic, I have frame, I don't know, they're symmetric, or they're transitive, or they're reflexive, or there are no conditions, just all frames. So I take an arbitrary frame. Then this implies that the fancy F belongs to the class of frames to which F belongs. So this and this have to belong into the same class of frames. Are we good there? All right. Thank you for the thumbs up. And this is when it becomes difficult for some logics because of the inherent way in which the frame condition is defined. you are not going to be able to have that in the canonical frame. So the problem is the following. Imagine you have a modal logic, and in that modal logic you have a frame, and these frames have certain conditions. What I'm telling you is that you have in QML, sorry, and completeness here is just to show that in the canonical model you can have all the formulas that you can derive. In QML, I'm asking you that if you have a frame condition on the canonical model, that frame condition has to be the underlying frame condition of the logic. So I have a small proof here of QS4. I now realize it would have been much better to do it for QK, but let's see how it goes. So the idea is that we consider QS4, and this logic contains this axiom. There are other ways of writing it, of course, but this is the most standard for me. So which corresponds to transitivity across the accessibility relation. That basically means, if you don't remember, so if you have two worlds that are related and that world is related to some other world, that means that the first world is related to the third world. So to show that QS4 is canonical, we must prove that the canonical relation RL is transitive. So our canonical relation said that two L places are related if and only if for all formulas which are necessary in gamma, then they are true. They belong to delta. And the proof of transitivity goes like this. It says like let these three be L places in the canonical model. Oh, yeah, sorry, I wrote it down there. So assume this and assume this. We must show that the first one can access the third one. So we start from this, and we need to arrive here. So since necessary phi belongs to gamma, and the logic contains the axiom for, and it's closed under deduction, it follows that this. So we're good. So since gamma is related to delta, by definition, any formula of psi such that necessary psi is in gamma must satisfy that is in delta 2. So if we let psi be necessary phi, we obtain that it is also the case that phi is necessary in delta. So, and since we have this one, and we know this bit of information, by definition, any formula chi such that box chi is in delta must satisfy that it is also in sigma, and if we let this there, then we obtain that it is also there. So that means that we started assuming that that box maybe doesn't work like that. So we started assuming that box phi is in gamma. Then we showed that this is in sigma, and we did it for two worlds for two L places for which there was this condition. So that means that we have finished the proof. And that the canonical frame is transitive. So what we're going to see right now is some of the logics which are canonical. And there is a big theorem that I'm going to skip that says that you have to trust me on this one. I think there's a sketch in the notes of what I'm going to say. Yeah. So this is a very brief thing. It says basically that completeness follows from canonicity, but I just need you to trust me on that one, or otherwise read the comment that I make here. But what it's if you are unsure of anything that we have discussed so far, what is important to me is that you remember what I'm going to say right now. And it is the following. The following is the fact that they are a class of canonical logics and there's a class of non-canonical logics. And it is easy to see how this works if we make a distinction between which axioms of modal logic make us look forward and which allow us to look backward. And forward also implies seeing yourself. So reflexivity is there's no problem. But where we're going to see is that the only possible way in which a logic is canonical, if its underlying frame, it is forward looking. And then I'm going to show you why it could be the case that something that is backward looking is non-canonical and hence non-complete. So if you apply some of the arguments that I told you before, you will be able to see that QK is canonical and hence complete. QT is canonical and hence complete. This is not supposed to be here. No, yeah, that's supposed to be here. This is Q4, not S4, but I have to correct this. So don't pay attention of how this is explained, but this is another system. Yeah, so basically this is S4. All right. So yeah, this is basically this one without T. Well, these are some of the famous canonical logics, and there are results that prove that these are complete, extraordinarily complete, but not all frame properties are preserved by the canonical model, because some of them require us to look backwards. And this includes the ones that have the axiom B. And if you know your modal logic, you know that S5 can be constructed in several ways, but you need B at some point. So B contains the B axiom, which corresponds to symmetry. So if I can look to you, you can look back to me. And S5 contains the Euclidean frames, which is basically an identity relation between the worlds. But what I want us to think right now is, why is it the case that some of these logics are not canonical? And it has to do exactly with what we're discussing about forwards and backwards looking. So give you a So remember that in the logic, we don't have either the canonical model of modal logic, nor we have the Henkin sets or the saturated sets. We have this thing called the L places. And to construct the L places, I show you how to do it, but I show you the condition for it. I didn't show you how to do it, but it is very similar to what we've done so far. So the problem is that L places do not behave as much as worlds as we would like to. Because in every L place, there should be, there are these Henkin complete theories. Maximally complete sets that are also saturated. But when we mix backwards looking conditions with L places, the problem arises. So let's say that we have an L place delta, and we have an L place gamma, and this place gamma, and here it is the case that diamond phi is satisfied here. Right? So, yeah, no, belongs here. So if that is true, then in the canonical constant domain model, what we need is a successor. So to gamma, such that it has witnesses in case. So if we say that psi is, there is an x. So if this is true, then we need a L place delta in which gamma belongs to it. Psi belongs to it. I'm going to start again. Sorry, I'm getting confused. So we start with an L place, and in that L place, we say that possibly psi belongs to it, when psi is an existential formula. If this is the case, and since we have the modality here, what we have to do is to construct a successor to gamma. And that successor to gamma is going to have to make it so that the existential one is there. And now, what I need there, what I need in gamma, or the Hankin condition, is that now I need a witness. And if you remember, this means that if I have an existentially quantified formula, I need a new fresh constant, which I haven't used before, so that I can create this Hankin set. Now, if I have a restriction that tells me that the frames are symmetric, the problem is that I build this in sort of downstream way. I look at the formula that I have, I see that it's a possibility, and I see that this is a quantified formula existential, and I see that I need a witness, and this witness, it is needed. So let's say that this is a witness in delta. The problem is that there is no guarantee that the witness chosen for delta is going to coincide. So there is no guarantee that the witness chosen for delta perfectly aligns, perfectly coincides with gamma. So the point is that if I put a new witness on delta, there is no way of assuring that this is going to coincide with an existential formula of the same shape in the original L place. So I cannot go and take a look back at which constant you used, because it has to be fresh. And if I have to make a new one and that is fresh in the other L place, then there's no way of assuring that these two are going to coincide. So if this is the case, then all the frame conditions that allow you to look backward are going to have a problem. And it is the fact that you will never be able to say that you have the same witnesses that satisfy the same formulas. So the problem with this, of course, is that if this basically shows that these logics are non-canonical, and therefore they are non-complete with respect to this method of doing completeness proofs. What is needed is some way of constructing the model such that we are able to do it. And in the notes, there is I talked something about quasi-canonical models, and that's still under construction. This is like an improvement on the canonicity proofs. So maybe we'll talk about it later in the course, but for now, I just want to leave you with two things. And the first one is this, the idea that so far we try to amalgamate both proof methods, and this came out good, but not so great. So we were able to get up to QS4. The idea is that we want to get to QS5, and we have not even added identity yet. So please bear that in mind. Identity is going to add huge problems for us because basically you saw it nowhere. So there's no way of straightforwardly saying, oh yeah, this is how identity works. You need some machinery that we're going to see next week. But the other thing is that there's other ways in which this canonicity proof can fail, and it is related not to the symmetry, but with how the canonical constant domain models are defined. And it has to do with the nightmare of all model logicians, the McKinsey axiom. And the McKinsey axioms, if you have ever seen it, I think that God created the McKinsey axioms just to fuck around with model logicians, because this is the source of every counterexample that when you have something working in modal logic, it's, oh, and here's the McKinsey axiom. Try that one out. And nothing works with the McKinsey axioms. So basically, the McKinsey axiom says the following thing, and we're going to denote it with M. It says that it necessary possibly by, then possibly necessary by. And at first glance, if you have never seen this before, you say, oh, yeah, okay, what is wrong with this? It just means you can swap. Well, the frame condition of this is called finality, and this basically says that there is an existence of endpoints. So every world can see a maximal world. So at every point in your model, there is a world which is an endpoint for which you can see it. So this is a problem, of course, for the canonical construction, because in the canonical construction, this is too large. There's an infinite ascending chain of L places that satisfy that you need to put into it. But then, because of the way in which we construct the canonical domain model, a fixed domain model, but you are never going to find an endpoint for each one. So if you want to work on QS4M, which is QS4 plus the McKinsey axiom, you're going to have to find a way to delimit this construction so that you can make it satisfy the axiom. This is just to tell you there's not the only way in which something fails to be canonical is not because of the backward looking, but there are more reasons in which this can fail. The first one is in how we construct the L places, because if I add a constant in the successor world, there's no assurance that that's going to be a constant that coincides with the original world. And the other one is this about how you construct the relationship between the L places. This is an ascending chain, and something like the McKinsey axiom needs finality for each and every L place. So with this, I'm going to stop there to see if there are any questions. All right, so let's leave it there. I'm going to stop the recording right now, and I'm going to ask Magnus, Isabel, and Ludovico to stay because they're on a special track. But I'll hope to see you tomorrow. Please stay safe, and yeah, have a great afternoon.